Hey, what is up, guys? Welcome back. Episode 110, I think today. Today is Saturday, May 3rd. Um, I think today's the day I'm gonna switch to Linux. I said this in a previous video, maybe about 3 or 4 days ago. I have been interested in switching to Linux the past about a month or so. Um, I don't really have any like specific reasons. I'm not like a huge IT guy. I just think. Um, I want to learn something new. I feel like it can benefit me as well, having knowledge about Linux and, having it as my main OS and learning. Back in the day, I used to be a huge gamer. I was playing all sorts of games, and I know probably Linux gaming probably isn't really the best, but, there's ways around it that requires, a lot of tinkering and messing around with settings and stuff to make the game work. And, some games don't even work at all on Linux, but nowadays, now that I've grown up a little bit, I'm about to turn 24 this year, so I don't really game anywhere near as much as I used to. Um, so I think today's the day that I am gonna switch to Linux. So um, I'm not even gonna dual boot. I know there's dual booting out there, but I think I'm gonna back up all my files today, probably after this video, and just install Linux on my system straight away. So I don't really know where to start. I was looking at Linux Mint, but then I was looking at Arch as well. But I know Arch is for like kind of tryhards from what I've seen, and um, I don't know. I saw the customization that you can do with it, and you can do some pretty cool things with it, but apparently it breaks all the time from the research I've been doing and stuff I see on Reddit. But yeah, I think that's probably what I'm going to do today, reinstall everything. This is probably like the third time I've reset my computer this year. So it's like, bro, I've reset my computer like 2 or 3 times this month. So I got to back up all my files again and, do all that. Probably on a Google Drive or something. That's probably what I'm going to do. I have my old computer over here, like collecting dust over here, and I think maybe I'm gonna boot Linux on that too. Um, so I don't know. Maybe run a double PC setup. Maybe I'll make it like some sort of home lab machine or something, or I can store files on it or something like that. I don't know. I haven't really decided yet, but yeah. I think today's the day. So I think the next time I record a video tomorrow, I'm gonna be running Linux. So that's gonna be a little different. There's gonna be a big learning curve to it too. So I don't know. I have a little bit of experience with Linux. I've been using it in a VM. I learned Linux kind of in a class, but I don't really feel like that's like real experience. I feel like I actually got to use the OS to get experience. I have basic Linux knowledge, but again, it's all just going to be a big learning curve. But I think if I, spend the next year learning Linux, I'll be pretty decent with it, in the next year. And I only think the support and everything's only going to get better. So, maybe a year from now, like, most games will support Linux. I don't know. I have no idea, but maybe most software too. I don't know. I have no idea. Besides the point, I think today's the day that I'm gonna switch. So we're gonna record a video. This might be a little bit of a shorter video. Maybe we're gonna do probably 1 or 2 problems because I just kind of want to get this done. So it's probably gonna take me all day to switch. I wouldn't be surprised. Probably installing everything, getting my system all customized and everything. So, yeah, maybe I want to do it on my other computer too. So I don't know. Might have to take a trip to Walmart and buy a few things. I don't know. I think I'm gonna need another Ethernet cable, to be honest. But yeah, I'm excited though. A little nervous as well because I don't really know Linux that well, so it's gonna be a big learning curve. But it'll be fine. You always, got to learn something new. So, yeah. Anyway, let's take a look. Let's take a look at our Pokemon of the day. We're at 110 today, so we have a wheezing today. Let's take a look at the sound. Oh, my headset's not on, jeez. I don't even know how to do this sound. There's our sound. Look, I got a shit ton of Linux stuff. Just been researching, but yeah. But yeah, let's take a look at some problems today. I believe this is our last 1D DP problem. Maybe we can take a look at this today. Oh, actually, let's take a look at our problem of the day, see what we got. Minimum domino rotations for equal row. We'll skip that for now. Let's take a look at partition equal subset sum. Give an array of nums, return true if you can partition the array into two subsets such that the sum of the elements in both subsets is equal or false otherwise. Can partition 1, 5, 5, and 11. Interesting. So my initial intuition with this problem is I feel like we generate all the different subsets, right? Okay, we generate all the different subsets and we store that in a set, and then we can look up each of the different sums in an O of 1 time. That's my initial intuition for this problem. I mean, I was pretty surprised that came like pretty quick. That was like literally looking at it for 20 seconds and I thought about that. So I feel like that's a pretty obvious intuition a little bit, but I don't know. I'm gonna confirm just to make sure that we're thinking the right way. Philistine partition equals subset sum. My initial intuition is why generating all the subsets is not efficient. Generating all subsets of an array of length is 2 to n possible subsets for each subset. You can compute its sum and check. So is my intuition brute force? Okay, I think mine is, this is brute force. We're gonna, if I was in an interview, this is how I'd solve this problem, so, or how I'd probably think about it for the brute force solution. Yeah, for recursion, we want to start at I. We probably want like a cur to come down here. We want to call recursion I cur. Inside of here we want a loop, so well, if I is greater than the length of nums minus 1. Then we want to cur.append I. We want res.append I. Make our res array over here. And then we probably just want to like return or something. Res.append. I guess we need to do cur.copy. Right? Otherwise we come in here, we do let's print res. I'm gonna come here, we want to do, okay, we want to cur dot then nums I recursion I plus 1 cur. We want to cur.pop, then we want to recursion I plus 1 cur. Let's take a look, see what that prints. This is just a basic backtracking. Cur is not defined. Oh, it's just one 515. Probably don't want the empty string, so if cur is equal to empty string, you just want to return. Why did that just do that? If cur is equal, oh shit, okay. We gotta do this in here. Okay. Instead of doing a res, let's make this a set. So let's do like hash is equal to set, right? We do, okay, well, res.append cur.copy. We would do, well, hashy.add the sum of cur. Let's see what happens here. Print hashy. One 5 6 10. Case 1 returns true because 1 5. How do we get 12? For what? How do we get 12 in here? Alright, we need res here. We need to print res. One 5 5 here, and then we get 11 by itself, right? Where is 11? We should get 11 by itself. 11. Okay. I'm just curious. Is it 01? It is, right? Yeah, that's what I thought. 01. Okay. Generate all the subsets. We append cur. Append cur.copy. So how does... So if we do, okay. Hash is equal to set. If we do hashy.add hashy.add cur dot the sum of cur. Print out hashy here too. Why does it not? I don't understand why it's different a little bit. Is it because we're not doing it code.copy? Is that why? It was never closed. Oh shit. Oh, okay. God, I'm so stupid. That's why. Okay, it's because when we're adding to the hash set, it's not replacing it. Okay, my gosh, I'm so stupid. Okay. How did I not realize that in the beginning? Okay. So hash.add cur. Okay, if cur in hashy, we just return true. Hashable list if cur in hashy. Okay. Sum val is equal to sum cur. Right now here we want to add sum val. If sum val in hashy, we just return true. List index is out of range. Let's just make like the flag. We'll make some sort of like flag. Let's do like flag is equal to false, right? We make flag equal to true. we have to declare it as non-local. Make the flag true, we add hashy. Let's see what happens now. Why is it out of range though now? What the hell? Recursion 0. Why are we getting an index out of range, bro? What the hell? Oh, because we don't have a cur anymore, dude. Why are we getting a list index out of range? Why are we getting a list index out of range? Missing the return statement, that's why. Okay. Return flag. Flag. Okay, let's print out hashy. I think we're calculating it too many times. Is that the question? That such that the sum of elements in both subsets is equal or false otherwise. Brute force way, we generate all subsets, compute their sums, and return true if any sum Oh my gosh, dude. Oh my.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve partition equal subset sum. So this is a pretty interesting problem. So we're given a non-empty array of nums containing only positive integers, we want to know if the array can be partitioned into two different subsets such that the sum of each of the subsets is exactly equal. Notice how that's basically saying if we can take one subset of the array, which is going to equal half of the sum of the entire array, right? Because if we partition it into two equal halves, right? Let's say the total sum was 22. If we partitioned it into equal halves, then each of the halves would be exactly 11, right? AKA one of the partitions equal half of the sum of the entire array, right? Because if we partition it into two equal halves, right? Let's say the total sum was 22. If we partitioned it into equal halves, then each of the halves would be exactly 11, right? AKA one of the partitions is going to be half that of the total sum. So for example, in this problem, the sum is exactly 22. So we want to know, can we get a partition or can we get a subset of this array? Basically, we can choose any of the values, and can we get a subset such that it sums up to 11? In this case, the answer is yes. It's true because we can take, the single 11, that sums up to 11, right? And obviously, if there's one way to get half of the sum of the total array, then the remaining elements are going to basically equal 11 as well, right? So you can see that 1 plus 5 plus another 5 is going to be equal to 11, right? Basically, these are the two partitions.
Okay, let's try that. So let's do, okay, well, half is equal to the length, the sum of nums divided by 2. Okay, let's print the half. Okay, we get 11. Okay. Just make sure that works. Okay. Def recursion. We have I and a cur, right? If I if I is greater than the length of nums minus 1, it would return, right? Our base. Okay, if I is equal to, actually let's just do, this is our target, right? Now if it's odd, we'd have to return false, right? So if, okay, let's do here, like if target is equal, target percent 2 is equal to 0, sorry, does not equal 0, we can instantly return false, right? Okay, we have our base. We have, okay, well, if dot append nums I. If wouldn't we have to append it first, right? So if the sum of cur is equal to target, then we can return true, right? And we can do, okay, well, recursion. Bro, why does it smell so bad in here? It smells so bad, man. One second. I don't know what that smell is, bro. I feel like it smells hella bad in here, bro. Anyway. Okay, if sum is equal to target, we return true. Otherwise, we do recursion. Recursion I plus 1. I plus 1 cur. Do cur dot pop. Recursion I plus 1 cur. Right? Recursion I. Recursion. Let's just like return our recursion. Man. Or sum of cur is greater than target, then we just return false, right? Not using the return value in both criticals, you're calling I plus 1 cur. Is ignored. Oh shit. We make our target. Target is equal to sum val divided by 2. Return true here if recursion I plus 1. Return true. Is this gonna give us a TLE? Yeah. False. Um, Otherwise, maybe we just like return false if it doesn't find it. All right. Let's take a look. TLE here, hopefully. Are we gonna get a TLE there? There we go. We got a TLE. Let's go. I believe this is our brute force solution. Let's double check. Is this brute force solution? Okay. Woo! We did the brute force solution. Okay, so now we need to add. Jeez. Dude, I still think something smells really bad in here, bro. Fuck it. Okay, so now we have to solve the we need the brute force solution. So we have the brute force solution, so now how can we add DP to this? I'm trying to think. Do something with I, right? So if I well, we're using I, so maybe if we've been to this sum before, we can return false. So maybe we make like a hash map here, and then we can check, okay, well, maybe we can check like if the sum of cur is in hashy, is in DP, sorry, we can just return DP maybe we should do the sum. Current val is equal to the sum of cur, right? So then we can reference it here, right? So if current val in DP, okay, current val, okay, then we can check, well, if current val in DP, we return DP current val, right? And this holds Boolean values, right? So then we loop through and we return, okay, make DP current val how would I do this here, bro? How would I assign this value here? Like, Fix. Use I_sum as a DP key. Why? Because the state is fully defined by the current index and the current sum. Okay, we're gonna have to do some recalculation here. So we got a recursion here. We keep track of our current sum, right? Okay, so we check. Okay, well, if our cur, get rid of this. If our cur sum is equal to target, I guess we can. We're not using the array anymore. We return true. If cur sum, okay, we can get rid of sum cur. If cur sum, then we return false. It's equal to true. If if I_sum in DP, then we can simply just return. Oh my gosh, dude, what is in my eyeball, dude? If I_sum in DP, then we can do, okay, well, if it's in DP, then we can just return DP I_sum, right? Yeah. Otherwise, we would do the recursion here, right? So we do, okay, well, DP I_sum is equal to recursion, right? I plus 1 cur_sum plus nums I, right? Is that the reference here? Nums I, yeah. Okay. Or recursion I plus 1 cur_sum, right? We don't include it. Then we would just return DP I cur_sum. Need a 0 here, actually. Where are we getting this? Not support instance of list and int. Okay. Okay, the OR here. Okay, that's what makes sense. The OR here, if one of these returns true, it returns true. But if both of them return false, it returns false. Both of them return true, then it's true. Right? So true. Think about what I learned in discrete math. Okay, that makes sense. Let's submit this. Oh shit, dude. I think we're starting to get the DP. Yeah. Which is good. Like, I'm starting to understand it a little bit. Got some 2 DP problems. Ugh. Let's take a look at some random problems on Leetcode. I feel like we haven't done that in a while. Just like picking some random shit. Let's add a new list. Enter list name. Oh shit. How do we look at lists on here now, dude? Ooh, there might be some contests today, dude. Starts in 10 hours. Wiki contest 448. Maybe I should do the contest tonight. I don't know. God damn it, dude. I don't know. Port to 10 will win a Leetcode water bottle. We'll win a Leetcode Big O notebook. I want to do a contest, dude. Maybe I should tonight. If I get it all installed, the Linux and everything, I'll think about doing a contest if I got nothing else to do. How we going with this Leetcode 75, dude? Counting bits, tree, search suggestion system. I'm gonna get back into some graph problems. How about we do that tomorrow? I'm just not feeling it right now. Let's check out this one. Smallest number in infinite set. Oh, these ones. Okay. You have a set which contains all positive numbers 1, 2, 3, 4, and 5. Implement the smallest infinite class. Smallest infinite class initialize the smallest infinite set object to contain all positive integers. In pop smallest removes and returns the smallest integer contained in the infinite set. Add back adds a positive integer num back into the infinite set if it's not already in the infinite set. To be honest, I'm not really too sure. I don't really understand. 2 is already in the set, so no change is made. Return 1, since 1 is the smallest number, and remove it from the set. So maybe we do, well, self.hashy. It says set, smallest infinite set. You have this set, so I'm guessing is equal to set. We pop the smallest. We add back. Add back adds a positive num back into the infinite set if it's not already in the infinite set. I think pop smallest is the priority queue. How to create priority queue in Python, dude. Heap queue module. Okay, let's import this here. Okay, how do we how do we heap queue documentation Python? How do we heapify again? Heapify. Okay, transform list X into a heap in place in linear time. Okay, heap queue.heapify. Okay, let's do like heap queue.heapify. Heapify list hashy. Is it? I don't know how this works. Okay, we heapify, right? And then since in Python we make Python heap queue. I think what is it called? Small heap or something? Does Python do min heap by default? I think it does. It's a min heap. This means when you function use heap up, the heap will be organized such that the smallest element is always at the root. Okay. So I believe that makes it easy for us, because now all I think we need to do is just heap q dot, is it heap pop? Heap pop. Heap q dot heap pop. Heap pop. Dude, is this like? Let's call it heapy. Dude, I don't remember, but heapy, and we return val is equal to. We return our val. This is totally wrong. Okay, heapy. Okay, this is where we meant to do it. Heapy is equal to heap q. Val is equal to heap q. Heapy is none. Passing a new list each time. Okay, we meant to. Okay, self dot hashy. Hashy is equal to set. Self dot heapy is equal to this, right? So then what we need to do is, okay, we do if self dot heapy. How do we? Self dot heapy dot heap pop. Okay, wait. Val is equal to heap q dot heap pop. Self dot min self dot heapy. And then hashy dot remove val. You would return val, right? Else, well, if there's nothing in heapy, we would just, I guess, return none, right? Pop smallest. Removes and returns the smallest integer contained in the infinite set. If self.heapy. Hashy dot remove val, return val. Return that. Right? Add back. Add the positive integer num back into the infinite set if it's not already in the infinite set. self dot hashy dot add. Okay, we have to check if it's in there first. Well, if num in self dot hashy, then we do self, then not in self dot hashy, then we do self dot hashy dot add num. Otherwise we do self dot heapy dot append. Maybe we heap push. Heap q dot heap push. Heap q dot heap push. What does it say? It's heap item. Push the value item onto the heap. Do the heap first. So a heap is heapy num. Heapy is not defined. Self.heapy. My solution to 2336 infinite set. So there's always something in the infinite set. If it's empty, you return 1. Return none when heap is empty. Track the next smallest number that hasn't been popped. What the? I'm honestly not. I'm really understanding this question well. I don't really get it, to be honest. Self.cur is equal to 1. Track a min heap and set for numbers that were added back because they were previously popped. Val is equal to self.cur. Self.cur plus equal to 1. Return val. Okay. That's what I'm missing here. If num is less than self.cur and num not in self.addedback, heap q dot heap push. and num not in self.hashy. We also need to check and num is less than self.cur. Bro, this is so stupid. Where in the... These things it does not say in the question. Let me explain why I added the changes. The problem description does not explicitly mention these details, but the key idea is that the set starts as infinite, beginning with 1, 2, 3. When you pop a number, that number is removed from the set. When you add back a number, it should be placed back into the set as long as it's not greater than the current sequence of elements. Okay, I think it's just a really confusing question, to be honest. That is just like interesting. I don't know. I'll be back though. I'm going to quickly go to the bathroom and then we'll do one more question. I'll be back in a second. Alright, what up guys? I'm back. Let's jump back into our Leetcode 75. Let's take a look. Maybe we do a binary search problem. Like it's been a while since we've done these. A peak element is an element that is strictly greater than its neighbors. 3 is a peak element. Given a zero index integer array nums, find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. So that nums minus 1. You may imagine that nums minus 1 is equal to nums n is equal to negative infinity. In other words, an element is always considered to be strictly greater than a neighbor is outside the array. Where the peak is 2, or index 5, 0, 1, 0, 1, 2, 3, 4, 5. It's still basic. Length array minus 1. While low is less than equal to high. I want to calculate our midpoint, right? And our midpoint is low plus, is it high minus low over 2? I think that's how you calculate the mid. So okay, we want to check. How do we want to move this though? We want to move. We have 1 and 1. I guess we want to check, well, if mid minus 1 and mid plus 1. That's how we check it, right? If mid minus 1 and mid plus 1. If mid minus 1 is less than mid, and if that is that, then we found our thing. But how do we move, right? How do we know where to move? Doesn't binary search have to be sorted? So wouldn't we have to sort this first? I'm confused. I thought binary search has to be sorted every time. Maybe there's a way we can do it without binary. Rotations with 162. Find peak element. Doesn't binary search always have to be sorted? If nums mid is greater than okay, let's do target found, right? So if nums mid minus 1 is less than nums mid, and nums mid plus 1 is greater than nums mid, then we can just return mid, right? Return the index value. If left. Okay, so if nums mid minus 1 is greater than nums mid, then we can move high to be equal to mid minus 1. But else if nums mid plus 1 if nums mid is less than nums mid plus 1, right? The peak must be to the right, so we'd move our low point, right? So we go, okay, well, low is equal to mid plus 1, right? Else if our nums mid is greater than nums mid is greater than nums mid plus 1, take a look at this. I can't wrap this around in my head, bro. Like,
I have to finish writing this paper. I'm swamped.
Just get Grammarly.
like I can't wrap it around in my head, bro. Like,
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, find peak element. We're given an array of integers, and they don't mention it here, it's mentioned all the way at the bottom of the description, but it's a very important fact, and it is that any two adjacent elements, suppose a number at index I and a number at index I plus 1, these are never going to be equal. So any adjacent elements in the array are not going to be equal. That's a very important fact for this problem, so I wanted to mention it at the beginning. We want to find a peak element within this array. A peak element is kind of how it sounds. So imagine that there are three elements. The peak element is the one that is greater than both of its adjacent neighbors. Now, it's possible that there could be multiple peak elements. That's okay. We can return any of them. So we could return this one or this one. Now, what if our array looks something like this, 3, 2, 1. At first glance, there aren't any peak elements in this array, but the way they define peak elements, these endpoint values, suppose 3, it's greater than its right neighbor, but it doesn't have a left neighbor. So can this be a peak element? Well, the answer is yes. Any endpoint value like 3 is implicitly assumed to be greater than its neighbor if its neighbor doesn't exist. So if its left neighbor doesn't exist, 3 is considered to be greater than its left neighbor. For 1, since its right neighbor doesn't exist, it's assumed to be greater than its right neighbor. Now, it's not greater than its left neighbor, so this is not a peak element, but 3 is a peak element. It's greater than this, and it's greater than this. Given those facts, we are guaranteed that there's going to be a peak element in this array. Our goal is to find it. It'd be pretty easy to do with a linear scan, but they actually want us to do better. We want to do this in log n time. Are there any algorithms you can think of that are log n time? Well, pretty much the only one that would work in this case is binary search. But is it even possible to run binary search on this problem? Well, let's go back to basics and think about what binary search is as an algorithm. We have an array, suppose 1, 2, 3, 1. Usually we have a left and right pointer. We calculate the midway point. Let's say this is the midway point. We have a pointer here. We check. Is this guy a peak element? Check its left neighbor. Well, it's greater than its left neighbor. Check its right neighbor. It's not greater than its right neighbor. So we know for sure this is not a peak element. But the idea behind binary search is that we should be able to eliminate half of the search space every single time. We should be able to either say, okay, we know for sure there's no solution on this side, so we're going to search on this side. Or we should be able to say the opposite. We know for sure there's no solution here. Let's search over here. But we can't really say that with this problem. There could be a solution here or here. And it's actually possible there could be a solution on both sides of the array. So let me say this slowly. This is going to be a modified binary search where we don't necessarily have to eliminate half of the search space every single time. We're just looking for a single peak element. So we just have to be sure that the side that we decide to search on, whether it's this side or this side, we have to be sure that the side does have a peak element. Maybe there's a peak element on both sides, doesn't matter. We just have to be sure that there is one on the side that we're searching. If this is not a peak element, how do we know which side is guaranteed to have a peak element? Well, let me show you a very simple example. Let's suppose that our array was monotonically increasing. So these points kind of represent the values of our array. Is this a peak element? No. Is this a peak element? No. Is this one? No. Is this one? Yes, it is, because it's greater than its left neighbor and it doesn't have a right neighbor. So this is a peak element. So if we were running our binary search on this array and we looked at this point, And we saw that this value is not a peak element, so we're not going to search here. Which side do we want to search, on the left side or the right side? We're going to go on the right side, because even though we can't see the entire array, we see that its right neighbor is greater than it. So maybe this is a peak element. Maybe this point doesn't exist and the value is actually somewhere down here. So we know this is not a peak element, but this is greater than its left neighbor and it's also greater than its right neighbor. That's a possibility. But even if it's not true, even if this value doesn't exist and it's actually all the way up here, look, it's still guaranteed that there's a peak element because all the way at the right. Either this is going to be monotonically increasing, which guarantees that there's going to be a peak element on this side of the array, or it's not monotonically increasing, which means one of these points, suppose this one is going to be down here, or maybe, you know, there's a few more points, and one of those is going to be below. So like this one would be all the way down here. And in that case, it's also guaranteed that this is a peak element as well as this being a peak element. Can you kind of see the intuition now? Either this portion of the array is monotonically increasing, which guarantees a peak element, or it's not monotonically increasing, which means that there's going to be a dip somewhere, which also guarantees that there's a peak element. And that's true because we know for sure that this is not a peak element, but its neighbor is greater than it. So it's already increasing here, and it might keep increasing or it might dip somewhere. Now, the opposite could have been true as well. It could have been going downwards. It could have been monotonically decreasing. So if we looked at this value and saw it's not a peak element, which side are we going to decide to search on? This side, because its left neighbor is greater, so we're guaranteed that there's going to be a peak element here because it's monotonically decreasing, which means all the way at the left is going to be a peak element, or there's going to be a dip somewhere, maybe here or maybe here, which guarantees that there's going to be a peak element. So if we are running binary search and our mid value, suppose in this case over here, is not a peak element, we're going to search on the side that has a neighbor value that's greater. And we're guaranteed to have a neighbor value that's greater, because if we didn't, if this was like 1, for example, and this is 2, and this is 1, then by definition, this is a peak element. So if this value is not a peak element, we're guaranteed that one of its neighbors are going to be greater than it, and that's the side that we're going to search on. It's really that simple. I know it's probably not simple to come up with, but once you understand it, it does make a lot of sense. So now, wrapping our binary search up, we're going to take our left pointer and shift it to be mid +1, so it's going to be over here now, and then we're going to recalculate the mid pointer to be left plus right divided by 2, which I think is going to be over here. So then we're going to check, is this the peak element? We're going to compare it to its left neighbor, it's greater. We're going to compare it to its right neighbor, it's also greater. So this is the solution. We return the index in this case, I believe. Yep, over here. And since this is binary search, it's running in log n time, constant memory. So now let's code it up. So
Okay. See if we can write this. Okay, so Okay, if mid. Okay, if nums mid -1 is less than nums mid, and nums mid +1 is greater than nums mid, we can return our mid, right? Else if our nums mid if nums mid +1 is greater than nums mid, then we can move our nums mid pointer. We can move our low pointer, low is equal to mid +1, right? Else would it just be the opposite? Nums else high mid -1. Let's print mid. Two. Wait. Let's print out mid here. So it checks. This is greater and this is less than. So if nums mid is greater than nums mid and nums mid +1 is less than nums mid, oh, really? That was it? Oh shit, this index is out of range. Else if nums mid +1. nums mid minus 1 if left is greater than 0, else float negative inf. Negative inf. Right is equal to nums mid plus 1 if right is less than or equal to nums less than or equal to the length of nums minus 1, else float negative inf. Mid minus 1. Left is equal to nums mid minus 1 if mid minus 1 is greater than 0, else should we push just one subtle bug. It's incorrect for mid is equal to 1. You're saying mid minus 1 is greater than 0, which is false when mid is equal to 1. So it incorrectly assigns negative int instead of num 0. Left is equal to nums mid minus 1 if mid is greater than 0. Okay, they're checking if mid is greater than 0. Okay, because if it's 0, then it's going to be out of bounds, alright? If it's equal to length nums minus 1, the right after it is going to be out of bounds. Let's see what...
So now let's length this. Most of them are going to show you at less than true. There is one edge case. What if m is equal to 0? In that case, is it greater than its left neighbor? No. So we are going to check that m is greater than 0. It's not equal to 0. It's greater than 0. And this is true. That also helps us because then we will never get an index out of change minus m plus is greater. Where either that means found the entire pretty efficient. If this was helpful, please like and subscribe.
that makes sense. Okay, cool. A little bit of a modified binary search, that's cool. Just think about it. I definitely need to do more binary search problems, but binary search here too. Is it? No. I think it is actually, yeah. Oh, Van. Yeah, this is our event solution. We're checking using 2 pointers. Okay. Anyway, appreciate you guys watching. I will see you tomorrow. Maybe it'll be on Linux. Probably will be, but we'll see. See you guys later.